My name is Joe Grand. I am a hardware hacker, an electrical engineer. I basically design stuff and break stuff. Today I'm going to give a talk about the JTAGulator, which is a tool that I've recently designed that will help you identify on-chip debug interfaces and useful things on pieces of target hardware. So I'll get right into it and explain everything as I go. I have a bunch of demos today and sort of intersperse the demos with some of the lecture. Since this is a 2-hour workshop, we actually have some time at the end of the lecture to actually get people involved. You guys can come up here and experiment. I have a few different JTAGulators. I have a few different target devices that you guys can plug into either with your laptop or my laptop and just kind of experiment with stuff. So part of the session is meant to be an open kind of hands-on experience. You can kind of play with new hardware and tinker with things that you might not normally get to tinker with. So that's why we have this extra time. So the agenda, we're going to go through kind of an introduction, look at some inspiration for the project, talk about identifying interfaces on a circuit board. So what are interfaces? How can they be located? Why are they even useful? And then once we find those, talk about why manually locating these interfaces is sort of hard and why a tool like JTAGulator is actually useful. Then I'll go into the design requirements and some of the actual hardware and firmware design details of the unit. I figure, a lot of tools that are out there are sort of these black boxes that you just get and you use, but the JTAGulator was meant to be an open source platform that you can build from scratch if you want, or build with, get a bare circuit board and assemble it yourself, and really just make it completely open and completely accessible. So I figure going into the details of the actual design and why it works the way it does will just help you understand the tool. And the better you understand a tool, the better you can use the tool. And then we'll go into specifically two different on-chip debug interfaces, one of them being JTAG, hence the name JTAGulator. That's an industry standard debug interface. So we're going to talk about that first, and then we'll also talk about UART interfaces, or asynchronous serial interfaces. So those are the two types of interfaces that the JTAGulator can currently detect, and then we'll, over time, hopefully add more functionality and kind of more features. Then we'll go into limitations, future work, and then open up for the kind of hands-on workshop. And we will take a break at 10 o'clock for 15 minutes. So on-chip debug interfaces are sort of a well-known attack vector in the hardware space. If you're hardware hacking, usually one of the first steps that you do when you're attacking hardware is you get access to the circuit board and you say, okay, where are there interfaces? Where can I connect to on the board that might give me extra functionality or might serve as a stepping stone for me to then do other things like extract data or manipulate the system? There's plenty of examples of recent hardware hacks of people using these debug interfaces. So it's sort of an Achilles heel, and vendors know that, but vendors and engineers need these interfaces to develop their product and to actually work with their product. So, they don't really want to remove them because it's going to make their job way harder. So we can take advantage of the fact that anything that's there for an engineer is going to be great from the attack point of view. So sometimes what vendors try to do, since they know that attackers and hackers are going to go after these interfaces, they try to obfuscate it in some way. Maybe they say, okay, we need to have our JTAG interface on there, but let's cut some traces during production once we're done programming the device, or once we're done testing the board, or let's remove some resistors from the board, or maybe they try to implement password protection, which is sort of, there's no standard for password protection on interfaces, so they just try to roll their own security. And usually, as we know, rolling your own security isn't good, and maybe there'll be other ways that you can find to defeat that password protection. The one problem is that identifying on-chip debug interfaces actually can be time-consuming. It can just be really annoying and potentially difficult, depending on the integration of the board, how much stuff is on the board, how much access you can get to different features on the board. And sometimes you might not have the equipment. You might not have the desoldering equipment, or the oscilloscope, or a logic analyzer that you might need to manually probe and try to figure out what interfaces are. So it sort of requires somewhat of an engineering skill set to figure out these on-chip debug interfaces. So what I wanted to do is make that a little bit easier and simplify the process to detect these interfaces and to bring more software-focused, non-hardware people into hardware hacking. And I think this is one of the first steps, is trying to get people, to use a tool that will give them something. And that's what a tool is all about, to kind of help them through the process. So I did have some inspiration for the project. There were a few things that had existed already as far as proving the concept of, can you enumerate through a bunch of different unknown test points on a circuit board and try different pin permutations to see if there's a debug interface there. But none of them were they were all kind of hacked together and not really suited for what I wanted to do. And I wanted to have a platform that I could kind of share with people and at least have a little more control of what it was doing. But Hunz's JTAG Finder was the first. He gave a presentation back in 2006 about having a set of unknown test points on a board and having a platform. I think it was a Atmel-based development board or something that he was using with some set of I/O pins. And he proved the concept that you could actually manipulate the pins and go through certain pin permutations to detect an interface. So that was sort of proved the concept, which was really cool. There was some other work, JTAG enum and RS-232 enum, by a guy named Dead Hacker, who gave a presentation at Chaos Computer Congress 2 years ago, maybe, that sort of refined on Hunz's work. But it was Arduino based, and Arduino is a sort of microcontroller platform, hobbyist microcontroller platform. It had limited I/O pins. It didn't really have the features that I wanted. It didn't have good input protection to protect the JTAGulator and also to protect the target circuit board that you're connecting to. Since you don't really know what you're hooking up to, you want to have good protection there. But it took it another step further. So I got some inspiration in that and said, okay, cool. I know it's possible. Let's try to make it a little better if we can. And then the DARPA Cyber Fast Track project, which was a program that was funding hackers and small businesses in the United States to do kind of novel research, like new research without having to deal with all the bureaucracy of the government. So I said, okay, cool, I'm going to try to propose developing the JTAGulator for this project and get paid to build stuff, which would be awesome. So I wrote this whole proposal, did all sorts of research on how the system was going to go together, submitted the work, and it actually got rejected. So I said, shucks. But by that point, I'd already done all the base research, so now it was just a matter of designing the thing. So I was like, all right, forget it, I'm going to do it anyway, and then I can share it with the world. So the first step that we need to do, regardless of if we have a JTAGulator or not, is look for interfaces on the board. Look for things that we can actually tap onto, solder wires onto, connect up to connectors, and see if there's something useful for us. Sometimes they will be, sometimes they won't be, and that's part of the hardware hacking process of kind of going through and narrowing down the important information. So first we'll look at external interfaces. These are things that you don't necessarily have to even get access to the circuitry for, which can be really handy a lot of times. Maybe on the first unit that you're hacking with, you have to open it up and see where the pins are and see how they come out. But eventually, if you can do an attack without having to physically open up the product, that just makes it that much cooler. So external interfaces are things that would be accessible to the outside world without having to go directly onto the circuitry. Those are normally things that maybe are hidden underneath a battery cover, underneath a sticker, because they're not intended for the end user. They're intended for the manufacturer during the manufacturing process, maybe to clip onto or plug onto once the device is built and assembled to do final programming or final testing. And then maybe they just cover it up in hopes that the user never sees it. So if we can find that, maybe that's something we could take advantage of. And usually it might be like a set of test points in a row, or maybe it's some proprietary connector. It all depends on the product. So some examples here. Here's like 4 pins on the back of a Garmin GPS unit covered by a little rubber cover. Here are 5 test points on the back of an RSA secure ID token. So it's like, oh, interesting. And there was a sticker over that, little black sticker. So you take that off. It's like, okay, is that an interface that I can use, or is that a read-only interface or a write-only interface? Who knows? This one here is from a Jawbone Up wristband, like the wearable wristband device, that there's a little button at the end that you can select modes. And that device is pretty cool. It's like a molded rubber wristband. But if you take this cap off, here's the button. There's actually 4 other connections on there. So you go, okay, that's probably the programming interface to program the microcontroller during the production process. Because if you think about the complexity of this wristband, there's like a rubber kind of sheath around it. So you can't program it. Once it's all put together, it's all nice looking, there's no way to program it. So the only way to do it, and usually you don't want to program the devices in a system that you're manufacturing until as late in the manufacturing process as you can, in case there's changes, in case you have to do firmware updates right at the end. So this is sort of the way that they can manufacture the whole product and then do final programming. But for us, if we detect that and we can then figure out what kind of interface it is, we might be able to take advantage of that. So moving to internal interfaces, these are usually, I guess maybe they're the same level. I was going to say they're usually easier to find, but it sort of depends. Internal interfaces are going to be things that are on the actual circuit board itself that requires you to open up the housing to get to. And that's not normally a big deal. I have a bunch of access points up here that are pretty easy to get access to. Either you unscrew the case or you crack the unit apart or whatever. But defined interfaces, we normally look for a few different kind of key features. One of them would be test points or unpopulated pads. And test points are copper pads all over the circuit boards that are put on signals that, interesting signals that the engineer might need or that a manufacturer might need. So you're not going to see test points on signals that are not important. You usually would see test points on things that are, like programming interfaces, maybe debug interfaces, maybe different voltages from regulators or something that they need to check during manufacturing. So we can look on a board and identify test points pretty easily to see, okay, those are probably good targets to look at. But even better, so say for this example, there's small test points, but then there's like these 4 obvious ones right in the middle, big fat test points right in the middle of the board. So I would say, okay, those are probably more interesting than the smaller ones. I'm going to look at the big ones first. Same thing on this side here. This is a BlackBerry device. There's a bunch of small test points all over the place, but then there's this big clumping of 6 plus that one right in that group. So naturally I say, okay, those are bigger, so bigger must be better. I'm going to go for those first. And that's just kind of the process. You can also take advantage of silkscreen markings, silkscreen being printed information on the board. So if we look on this one, this was from a cordless phone. VBAT, ground, I2C clock, I2C data. Now I know right away the engineer put those markings there to help them and to help the manufacturer. Now I know that that's an I2C interface. It's an inter-chip communication interface that now I can go and clip down with my oscilloscope or my logic analyzer and actually start sniffing information that's being transmitted across that bus. So sometimes it's really easy and they actually give you, good information. Other times too, if the test points are in an easy to access location, that also sort of gives it away. A lot of times we'll see the connectors on the ends of boards. So I'm not going to switch to the camera for this, but you can come up and look. So for example, like the JTAG interface on this access point is right in the upper right corner. So it's kind of away from all the other stuff to make it easy to access. Same with like this BlackBerry device there along the bottom behind where the SIM card was. So it's sort of out of the way but easy to access. So normally we would look around the edges first and then sort of move in from there. Other times, the pinout is based on like a common format or maybe an industry standard format. So it's not just a bunch of random test points or like an unknown grouping, but it's something that's actually, you can go online and verify pinouts. So sometimes it would be like a single row pinout, sometimes double row. The most commonly used would be like a JTAG interface, which again we'll talk about more later, where you can go to this website, jtagtest.com, and look at different common pinouts for different architectures. It doesn't mean that the engineers are going to use those pinouts, but it makes their job easier, right? Because if they just use a standard pinout, then their standard development tools are going to work on it right away. They don't have to create some interface module to make it harder. So a lot of times we'll see just a standard interface that we can just plug into with JTAG hardware, not even needing JTAGulator at all, because we already know the pinout, plug in and go to town. So this example over here is from Barnaby Jack's ATM hack from Black Hat 2010. And part of his research was figuring out how to get access to the ATM. And it was a Windows CE based platform. And he opened up the unit, and inside there was actually a connector right there, JTAG connector, standard, industry standard pinout. So all he had to do was buy an off-the-shelf JTAG adapter that supported that architecture, plug in, and continue on with his attack. So he didn't have to do any searching to find the interface. It was right there and very obvious. Same thing on this side. This is from the Xbox. Here's a low pin count debug connector, LPC. In this one, we see pin 1. which has the arrow. It's also, pin 1 is usually denoted by a square pad as opposed to a circular pad. So we can look on the board and say, okay, that's unpopulated. We would still have to suck the solder out of these holes and then put a connector in, but we didn't have to do a lot of work to figure out what it is. And the LPC debug is another one that's sort of a standard pinout. So sometimes we get lucky, sometimes it's easy. You can also use kind of PCB layout heuristics to get an idea of maybe which connectors might be interesting ones or might contain some sort of bus. So we can take advantage of the fact that similar traces are grouped together. So if we look on a board like this, there's other little traces and stuff and some other pads around there. But then we see this big grouping of traces coming up to this connector at the corner. So right away you can say, okay, the fact that all these traces are going up together probably means it's some sort of similar interface. Maybe it's a bus of some sort, or maybe it's something else. But all those traces going together is something that's a clue that that's probably where we want to attach some points of the JTAGulator. On the other slide, here's a picture of another access point I was looking at. This connector wasn't here. I put that on later. So just imagine that there's just an unpopulated footprint there. But there's these resistors connected to some of the pins. So sometimes you can actually look at a board and say, oh, okay, there's a bunch of resistors next to this unpopulated connector, or a bunch of resistors next to this group of test points. That might be an interface, because resistors, either pull up or pull down resistors, are used to set the static state of a system or of a bus, sort of the unused, kind of idle state. So when I saw that, I saw, there was a few other connectors on the board, but I saw this one with the resistors right there, and it just seemed very obvious to me, and that ended up being the JTAG interface. I didn't know which pins, but that's where the JTAGulator came in, right? So I could at least identify it and then go to the next step. Other boards try to be a little more sneaky, covering the interface with solder mask. And solder mask is a coating that goes on top of the board to protect any copper areas that don't need to be exposed to the outside world, like for, that don't need to have components soldered onto them. So here's a connector, two different connectors actually, with the solder mask on top. So the only way you can get access to the actual copper and make contact is to scrape off the solder mask. So it seems like maybe during manufacturing, or maybe during development, that area was exposed, so developers could have some connector plugged in or something like that, and then they just changed the solder mask plot when they were manufacturing their boards to just cover that over. That's a very kind of low cost, easy thing to do. Changing the mask is not a big problem during manufacturing and during PCB fabrication. So maybe they did that to cover it up, knowing that end users aren't supposed to touch those things. Same thing on this side. This is from a Peak two-way email device that was on the market for a few years. This was once you take apart the housing, there's these tiny, tiny little test points, all covered in solder mask. So you have to very carefully scrape those off, solder wires down to it, or maybe you could create a little test fixture and have some pogo pins, spring-loaded pins that could touch down on all of those test points, which is probably what the developers had, and then figure out what they are. So that gets a little bit harder, right? Because if they put solder mask over it, what if instead of having this very obvious connector-looking thing, if they were just smaller points that maybe looked like vias, which are connections that go through the board, it might be really hard to figure out what's a legitimate test point for an interface versus what's just a normal, connection on the board that we don't care about. So it gets a little bit harder, and you might have to then do additional reverse engineering to try to narrow down your search. Another thing that some vendors try to do is, instead of using connectors at all or test points at all, are using existing part packages. So in this case, there's 4 resistor footprints, but these are the actual JTAG connections. So it's security through obscurity, right? On the board, when you look at it, you don't know which components are there or which components are missing intentionally or which ones are there to obfuscate an interface. You just don't know. But once you find out that these are the interfaces, that those are the interface pins, that's not going to change for any revision of the board. So it's totally just security through obscurity, and it only takes one person to find that and then release it on a website for everybody. But it does make it way harder. And that's where the JTAGulator comes in. So once you do find the interface, the kind of traditional way to do things, manually determining pinouts, is you'd first look on the board, you'd find your connectors like we talked about. Then you try to trace out where they go. Now usually there'd be like a main microcontroller on the board somewhere that's very obviously marked, or it's towards the center of the board. And usually the connector, you'd want to see if it goes back to that part. So you could visually trace things, use a continuity tester or multimeter in continuity mode to check connections, and see if you can get it, trace them back to the part, and then use a data sheet to correlate those pinouts. Sometimes, though, you can't get access to the part if it's a ball grid array device, which have solder balls underneath the part as opposed to pins that come out. So it's a lot harder to probe what's going on, and it's a lot harder to see what's going on. Then maybe you need to use X-ray, which is common with contract manufacturers. You can go and stick a device in an X-ray machine and see where traces come out, see where they get broken out, and see if you can follow those to the connectors. Maybe you have to remove the part from the board, remove the BGA part so you can actually see where things are going. There's lots of ways to do it, but that's where things get difficult if you don't have the experience and you don't have the tools. And then you can also, probe the connections, use an oscilloscope, monitor what's going on, trial and error of pulling pins high and low and seeing if that kicks off some sort of process with the other pins. It's just a very long process, and that's the whole goal of the JTAGulator, is to simplify that process a little bit. So the design requirements for this tool, as I talked about, open source, has to be open source, has to be hackable. In this community, that's just, that's how we make better products, is have things open, have people be able to look at the design and comment on it, and look at the firmware and comment on it. I'm proud to say I learned how to use GitHub to upload my firmware, so it took me a while. Being a hardware guy, it was a learning curve to figure out GitHub, but I did it. And that way everything can be shared, and it's a really cool thing. A lot of the products that I design, especially the hobbyist types of modules, I like to have very simple command-based interfaces, so you can hook up, enter some commands, to see a list of commands, and just kind of interact with the device in a very easy way. So I wanted to have a simple interface, which we do. Proper input protection, and I'll talk about some of these features in detail, but input protection to protect our board from getting damaged from voltage levels and from things that we're not sure about on the target board, because we're connecting up to a bunch of different test points on the board, and they could be negative voltages, they could be higher voltages to drive an LCD or to drive a motor or something. Like if we're just arbitrarily hooking up to test points, which sometimes we do, we need to make sure that we're protected, that the JTAGulator is protected, that your machine is protected. So if you hook up to something potentially bad or potentially damaging, it's not going to actually damage stuff. Adjustable target voltage. Lots of different systems have different system voltage levels. So things like, say, the DEF CON badge that I have here that I'll show a demo of, that runs on a CR2032, a 3-volt lithium coin cell. So that's a 3-volt system. Mobile phones maybe are 2.6 volts or 1.8 volts. Maybe they're getting even lower now. So we want to have some sort of way to properly communicate and properly have the levels that we're sending from the JTAGulator meet the specifications of the target board. Because the JTAGulator system is a 3.3 volt system, because that's what the propeller processor runs on, and that's what we're using. So we need a way to kind of convert that and make sure that we don't damage any signals going out and any signals coming back in. Off-the-shelf components, part of being hackable, right? Being able to just get components from DigiKey or from a market or whatever. So just we're using very common parts. And then you could hand solder it. It's a two-sided board. The Gerber plots are available online, so you could fabricate your own board somewhere. You can hand solder the parts. Some of them, most of them are surface mount, and some of them are pretty fine pitch, but you can do it. It's great practice, actually. If you want to have a good project to really learn surface mount soldering, this would be the one. I built 4 of them by hand, and I'm never going to do it again, but still good practice. All right, so we'll go into some details of the hardware. Here's just a kind of general block diagram, and I'll go through some of the details. But we have as the core a parallax propeller processor, which is a really neat kind of 8-core processor. Used a lot for hobbyist applications and industrial applications and sort of low volume, very interesting, complex systems. So that was a fun one to kind of hack with. And Parallax is a manufacturer of electronics, designer of electronics, mostly hobbyist, educational. They do a bunch of stuff, and they sell a bunch of my other products. So I was like, okay, well, this is a cool kind of hackable part. Let's use it. We have USB coming in, a mini USB coming in. That's going to provide power to the JTAGulator, also serve as the programming interface to program the propeller processor, so when we do firmware updates, and also to serve as the actual user interface to us through a terminal program. So it will show up as a virtual serial port. Double EEPROM for firmware storage, our level translators, which are for the adjustable target voltage, input protection circuitry, and on the other side we have a digital to analog converter that we're generating our adjustable target voltage from 1.2 to 3.3 volts. And I'll get into detail of that. But it's pretty much like a kind of a basic system. If you look at it, it's really the CPU with a bunch of protection on 24 channels. So it's a very kind of generic board that you could use for all sorts of other stuff as well, which is why I love it. So here's the board. It's very pink. I figured, with a name like JTAGulator, we got to have a very pink board. It kind of offsets the heavy metalness of the JTAGulator name. And I figure a pink circuit board is going to be a lot harder to lose on your desk. Right? If you have a green board, it kind of blends in with everything else, but pink will stand out. So you'll always be able to find your tool. But here's what it looks like. If we start on this side, USB coming in, status indicator up at the top will be red or green depending on what's going on in the system. Our op-amp circuitry is down here. Level translators, input protection, and then here are the probes, or the interface connections. There's two different ways that you can connect to it. One is going to be through the screw terminal blocks at the top. So if you have flying leads or wires coming in, you can just screw down to the terminals on the top. The bottom are 2x5 row headers that are compatible with the Bus Pirate probes. And when we switch to the camera, I'll show you closer what they look like. But it's basically just an off-the-shelf set of probes that have a little connector on it with a bunch of test leads on the other side. And the Bus Pirate is a kind of hobbyist hacker tool to let you interface with serial devices and manipulate serial devices. And that's another open source tool. But because that's been around for so long, there's these cables that are available everywhere for like $5 or $6. So I figured, okay, let's use these because then you can just clip down, plug this onto your JTAGulator and you have a bunch of test clips that you can clip onto a target board, which is kind of cool. Having two interfaces as well is useful if you want to hook up like a logic analyzer or kind of sniff what's going on at the same time, because then you can connect your target on one of them and then connect up to the other ones to sniff. So it's kind of neat. So I'm going to get into some details of the actual hardware subsystems. The propeller, as I mentioned, is an 8-core architecture. Very, very neat. Completely designed from the ground up. So Chip Gracie is the guy that started Parallax, and he's a hacker in the truest sense of the word. And he was sort of tired of having to deal with these proprietary chips and deal with semiconductor manufacturers that don't give out all their information. So he's like, I'm going to design my own chip from the ground up. So he, built his own registers and CPU and everything. And it ultimately, after 6 or 7 years, turned into the propeller. So it's just a really neat chip. There's lots of information about it, lots of very smart people on the discussion forum sharing information. There's a site on the Parallax site called the Object Exchange, where people can write modules and write different programs for the propeller and upload them. So it's sort of like, if you look and it's like, I want to have LCD control, or I want to have an FM transmitter, or I want to output composite video. You can go online and look through the Object Exchange and sort of grab objects. Objects are basically like header files or functions. Grab those and sort of integrate it into your design. So it's super cool. So, in reality, you could go to the Object Exchange and look stuff up and say, okay, I want to add a VGA output to the JTAGulator and hook it up to a standalone terminal, standalone monitor or something. There's just all sorts of stuff you could do. So I just loved the community support aspect of it. You can code in Spin, which is a not proprietary, but a custom language built specifically for the propeller. Sort of a high-level, kind of like Pascal, C sort of combination mashup of stuff. A little bit of a learning curve to figure it out. That's what the JTAGulator is currently all written in Spin. So it's at least easy to kind of look through and read comments and see stuff as opposed to assembly language, which tends to be a little bit harder. But you could write it in assembly language. Also, you can write it in C. Parallax is creating a tool right now, a cross-platform tool to be able to write in C. But right now, everything is done in Spin. The system normally runs at 80 megahertz, which seems slow when you compare it to like a Linux-based thing or a mobile phone or something. But really, 80 megahertz for like a standalone hobbyist type of microcontroller is pretty good. It's pretty fast. And you can actually overclock it to 128 megahertz with pretty good reliability. The way the system's set up is you have some global memory, which is called hub memory, that's shared with all of the 8 cogs. So there's 32K of RAM. The ROM is actually a masked ROM, which has the bootloader and character set and some other stuff specific to get the propeller up and running. So code basically gets loaded from an external EEPROM on power up and then executes out of RAM. And then the remaining portion of RAM after that is used for the stack and for variables and things. Shared memory. And then each cog has its own 2K of RAM as well. So you can have a cog kind of executing its own stuff and using its own memory, and then maybe once in a while dumping things to the main memory if you want to, if you need some other cog to access it. For the JTAGulator, we don't really have a lot of complex stuff going on with cogs, but there is just lots of capability there. 32 I/O pins with 40 milliamps, sync or source current per pin. And one of the things I wanted to do when I was designing this tool is find a processor that I could use that had lots of pins, but also had an easy way to program it and didn't need this, weird, large development environment and all of this stuff. So trying to find that balance. But 32 pins, we're using 24 of those pins for I/O, and the other stuff we're using for the analog to digital or digital analog converter and stuff. So it's sort of it's a pretty good number. You could always design a similar JTAGulator with an FPGA with 128 pins or something. So you could potentially get larger I/O, but I think 24 is sort of a good number for now anyway. So the standard development is done with a tool called the Propeller tool, which actually is in the Black Hat materials on the DVD. So if you want to load that up and kind of play with it and load the source code in, you can. Right now that is Windows only. So I mentioned that they are doing a cross-platform version for C, but they're also creating a cross-platform tool that will let you write spin on things other than Windows. But for now, it's all Windows-based. And we program the device through that same interface that we're using as the user interface. And that's just one connector in. We don't need to do a lot of stuff if we want to program. Because again, remember the intent is to get non-hardware people involved in this stuff. So it has to be easy. Here's just a block diagram of the core. And from a circuit point of view, there's really not much there. We just have the main part, 5-volt external oscillator. And the loading capacitor is actually internal to the propeller, so it's just one less thing to have to deal with, or two less things that you have to deal with, because normally you need 2 capacitors. So just sort of saves things. You can just throw on a 5 megahertz crystal and be good to go. And there's not much else, just the external EEPROM. So this is a very simple to get up and running. For the USB interface, sort of serves multi-purpose, which I love. It powers the device and then lets us program and serves as a user interface. I'm using an FTDI FT232 device, which is a standard USB to serial interface. So when we can send TTL level serial from the JTAGulator, 0 to 3 volt signals. This FTDI part's going to convert that into proper signals and also show up as a USB virtual COM port on your machine. So it will work with Mac, PC, Linux, whatever, Windows, whatever you want. Anything that supports USB virtual serial ports, virtual COM ports, and there's tons of different drivers on the FTDI website. Anything that supports virtual COM port, you'll be able to use this thing with. Possibly even maybe Raspberry Pi at some point, I don't know. Part of the USB interface that I wanted to make sure that we did properly was have a power distribution switch. A lot of times you'll see products that just have a USB connector going straight from the board directly to the target computer. And if you look on the actual inside of the board, the power is shared between 2, right? Because USB provides power. But you're supposed to actually have kind of a proper enumeration process to make sure that you don't potentially try to sink too much current from the target, and make sure that the computer properly knows that you're properly enumerated and it knows what kind of current you're expecting before it provides it to you. So as part of the USB spec, you actually need to kind of power up properly and enumerate properly when you plug a device into a computer. Most things out there, very cheap devices, don't do that. So technically they're not USB compliant. But I wanted to at least have a way that if there was some problem with the JTAGulator, or you had it hooked up to some board that was just causing it to suck so much current out of a device, that it would fail properly and it would kind of disconnect itself from the system. So we're using an MIC, a Micrel MIC 2025 power distribution switch, which basically what we're doing is disconnecting most of the circuit from the system, and when you plug in the JTAGulator, only the FTDI part gets powered up. So the enumeration happens properly with the target, and then once it's enumerated and the FTDI part says, I need 500 milliamps, then the PC will give you that current, or at least allow that amount of current to be drawn, and then it will enable the rest of the system. So here you can see like VUSB is when we plug in to USB, that's the 5 volt line of USB. We're only powering the FTDI part, and then once everything's good, one of the pins on the FTDI part says, okay, we're all enumerated, let's enable the rest of the load, and then we enable a low dropout linear regulator to enable the 5V0, which is the 5 volt line that will then go and feed the rest of the JTAGulator system. So it's just a good thing to do, proper kind of power up. So you can know with pretty good certainty that when you plug this thing into your computer, it's not going to blow up. Hopefully. Okay, so the adjustable target voltage. This was just a way, I needed sort of some way, to create this adjustable voltage that we can connect to different targets. So what I'm using is a pulse width modulated signal, PWM, on one I/O line, or one output line of the propeller. And basically the duty cycle of the PWM corresponds to the output voltage. And what I have is a lookup table with different duty cycles that I've measured out and measured the kind of resulting voltage. And now we have 0.1 volt increments from 1.2 to 3.3 volts, depending on target voltage. And the way that works is I have an op amp, basically an RC filter going through a buffer to provide the voltage. And we really don't even really need the buffer, but that's going to provide us a little bit of isolation and also give us additional output current, because that op amp can provide about 150 milliamps of output current. So it sort of acts as this amplifier for us, where now we have a voltage, but we can also source some amount of current in case we want to use this VADJ line, the adjustable target voltage line, maybe to control the target or turn on the target or control another piece of circuitry or something. Gives it just a little bit more of a kind of future expandability by having this buffer in here, and it's just safer that way too. So it's just a single supply standard op amp. For level translation, this is going to allow the 3.3 volt signals from the propeller to be converted to whatever our adjustable target voltage is. We have the TXS0108E, which is a very common bidirectional level translator. So it will take in 3.3 and then output it at whatever voltage we're putting in on the other side, which I'll show you the schematic of that. The cool thing about this part is it has high impedance outputs, so we can use the output enable line to essentially keep all of the I/O pins that might be connected to a target board high impedance, which essentially disconnected from the system or from those connections until we're ready to start JTAGulating. That way, as we're plugging things in, we're hopefully not going to screw stuff up, because the target doesn't really know that they're there yet until we enable the output enable, and then those pins go high or low. So having the high impedance is really kind of a useful feature. And there's not much to it. Pins coming in, pins going out. For input protection, we have current limiting resistors and diode clamps to prevent overcurrent and overvoltage of test points on the target board. Because we don't know what we're going to connect to, we need to protect ourselves there. To an extent. There is a range above some voltage that things will get damaged, but it's still going to protect us a lot. So what we have is from each target on each channel, resistor coming in, and then a resistor going, or a diode going high and a diode going low. So those are called diode clamps. And what those do are basically clamping voltage to a fixed level, which would be positive. It's going to be the forward voltage of the diode plus whatever the adjustable target voltage is at that point, so 1.2 to 3.3 volts. And then for the negative side, it's just going to be the negative forward voltage of the diode, so the diode drop. And the diodes that we use are Schottky diodes. Since we need 48 of them, 2 per line. Having individual discrete diodes would just sort of be a pain, especially if you want to hand assemble these things. So I found these diode arrays, which are sort of cool, that are actually designed for diode clamping and for ESD protection, where each I/O line has its own diode going high and own diode going low. So now we only need, there's 4 channels per chip, so we only need 6 of them. So it's slightly better. That's pretty much all the hardware. For the bill of materials, there's mostly discrete components and resistors and stuff, but total cost is around $50 US. If you wanted to buy one, single quantity, $50. The more you buy, the cheaper parts are. Here, this bill of materials is from DigiKey, which is a fairly large parts distributor worldwide. And then the full, PDF is on my website if you want to see it better. So from the firmware side, currently this is kind of the source tree that we have. JTAGulator.spin is the main spin file that handles all of the initial state machine and the setup and everything. And then I wanted to keep things modular, so as I add new functionality or new protocols, I have that as a separate spin file. So you have the parallax serial terminal, which is one of the default spin files to enable user interface, so to enable a serial interface for a user. So I'm using that for the user interface. Real random is a pseudo-random number generator based on some PLL jitter of the CPU that we use for the bypass scan test, which I'll show you. Then prop JTAG is all the low-level JTAG interface stuff. And then JDCOG serial is the low-level additional serial port that I'm using for the UART detection. So it's sort of, as you add more stuff, maybe the tree gets wider or anything, but right now it's pretty simple. And you can think of like these other spin files as just kind of extra header files or something, even though they're actually extra C files, I guess. There's still plenty of space left on this thing, even with all of my horribly, probably bloated and not very efficient code. We're still only using 1800 longs, 32-bit values. So we still have quite a bit of space available. So all the blue, lots of space for extra stuff later. Okay, so we're going to take our break now. I think that's going to be a good time. We'll take our break now until 10:15, come back and look at the actual details of on-chip debug interfaces, so JTAG and UART, and then we'll open it up, do the demos and all of that.